Your API just got 10,000 requests in 1 second from your user. Your server is down. Every legitimate user is getting a 503. This isn't hypothetical. This is what happens when you don't design your rate limiter correctly. Welcome to Scalable Architect. I am Anirban. Today we are designing a rate limiter that actually holds up at scale, the algorithms and the distributed state problems, and how real systems like Stripe and Cloudflare solves it. The algorithms. There are 4 algorithms. Each one breaks differently. The first one is the token bucket. Tokens are added at a fixed rate, say 10 per second. Each request consumes 1 token. No tokens left. Requests are rejected. This allows bursts, which is why AWS and Stripe uses it. The second one, Leaky Bucket. Requests can arrive at any speed, but they are processed at a fixed rate. No bursts, great for protecting downstream services. The only downside, busted traffic doesn't get rejected. It gets delayed. The third one is the fixed window counter. Count requests per user per time window. It's simple and fast and broken at the boundary. Let's suppose 100 requests at 59th second and 100 requests at 1 minute 1 second. That's 200 requests in 2 seconds. And your limiter thinks everything is working fine. And the fourth one, sliding window log. Track every request timestamp. Count how many happened in the last 60 seconds. Very accurate, very expensive. You are storing a full timestamp log per user. Where does the state live? The algorithm is the easy part. State is the hard part. The first one is the single server. Can be implemented using an in-memory hash map where each user ID maps to its current token count. When a request arrives, the server checks the user's token balance, allows the request if tokens are available, and decrements the count. Since everything is stored in memory, the lookup and update operations are extremely fast. The second one is the multiple servers. Now you have 20 servers. Let's suppose server 1 sees 3 requests, server 5 sees 4 requests. Actual count is 7. Neither server knows that your rate limiter is broken. Now coming to the third one, Redis as a shared state. Move all the state into Redis. One source of truth. Problem solved? Not yet. Coming to the last, race condition. 2 servers read the counter at the same time. Both see 99 out of 100. Both allow and both increment. User just sent 101 request. And the fix is atomic operations. Redis INCR is atomic. Read, increment, check all in one operation. For token bucket logic, use Lua scripts. Lua runs atomically inside Redis and no race conditions are there. Distributed rate limiting. Now you are global. US East, US West, Europe, Asia, Australia, these all are the regions. If you kept centralized Redis, every rate limit check is cross region. That's 100 to 2000 nanosecond added to every request. It's unacceptable. If you local Redis per region, the latency will be fixed, but now counters are split. 60 requests in the US East region, 60 requests in the Europe region. Each region thinks you are under the limit. User sent 120. You are leaking. Now coming to the approach 1, sticky sessions. Always route a user to the same region. One Redis sees all traffics and it works until that region goes down. It also creates hotspots. The approach 2, eventual consistency. Each region tracks its own count, periodically syncs to a central store. You accept slightly over allowance in exchange for low latency. Coming to the Cloudflare sliding window approximation, instead of exact timestamps, previous window count, current window count, weighted by how far you are from the window. It's not perfect, but it's cheap, fast and good enough for millions of requests per second. And the Stripe approach is simple. Decentralized Redis cluster, aggressive replication, all regions point to it. Higher latency, but financial APIs require correctness. Rate limiting at a scale is a distributed systems problem. The algorithm is 10% of the work. The other 90% is state, race condition, and choosing between correctness and latency. Subscribe if this was useful. See you in the next one.